So I am Azzam Haidar, and I am a senior engineer at the mass library team at NVIDIA. And today I'm going to talk about Tensor Core Accelerated Iterative Refinement Solver and its impact on scientific computing. From the title, I think you guessed, I'm going to talk about high-performance computing solver that take advantage of NVIDIA Tensor Core GPUs in order to provide a fast solution, time to solution. So, and since we are talking about a parallel, what I did something in a parallel right now to avoid squeeze timing. So I did a recording of the slide. I hope it worked. And I can be on the other laptop answering question live on YouTube. And then to maximize the 5 minute, I hope it worked. So let me start sharing. This is working here, seem to be.
Of Tensor Core NVIDIA GPUs. Tensor Core started with the NVIDIA Volatile V100 GPU. If you look here, the Tensor Core can deliver a performance up to 125 teraflops in half precision, compared to about 8 teraflops in double precision. They are extremely powerful units. That's amazing. By the way, it is worth to mention that the Tensor Core units here are mixed precision. The multiplication is done with no loss of precision, and the accumulation is performed in FP32. And that's being an important difference from doing it in standard FP16 FMA. Since here we are talking about NVIDIA A100, let's take a look to the A100 spec. First of all, in this chart, as you can see, the half-precision Tensor Core doubles its performance and can deliver a performance up to 312 teraflops today. The A100 also supports other precision or type. It supports the bfloat 16 and a new compute type that we call TensorFloat 32, TF32. The A100 has also FP64 Tensor Core unit, but it is IEEE compliant and does not involve mixed precision. Originally, Tensor Core have been developed for the use in artificial intelligence. But now, look at these numbers here. Look at this tremendous amount of performance that this mixed precision Tensor Core can provide compared to FP64. It's huge. So our main question now is, can we harness the mixed precision Tensor Core and take advantage of them in high-performance computing? In many high-performance computing applications, solving a linear system is the most consuming part of the simulation. So, accelerating the linear solver could have a great impact on the behavior of the application. How do we solve a linear system of the form AX equal B? The way we solve it is we take the matrix A and we transform it to a nice form, a lower and an upper triangular form. Then, solving it becomes a very easy task of back substitution with L and with U. This process of transforming A into a nice form is called LU factorization. Let's quickly go through the LU factorization, how it operates. The LU consists of a panel followed by a triangular solve, TRSM, and a gem. What is gem? Gem is a matrix-matrix multiplication. The interesting part here is that the cost of the LU factorization is dominated by these gems. And if you remember from the early slide, what are Tensor Core made for? Tensor Core are made to perform gems. Let's look back at the performance of those Tensor Core. We have the TensorFloat TF32, which can provide up to 156 teraflops. The half precision FP16 and the bfloat BF16 both can deliver up to 312 teraflops versus 19 teraflops for the FP64. So think about it. Let's take these gems and run them on the Tensor Core with TF32, FP16, or bfloat. They're going to run maybe 7 times faster. So our LU will be way faster. So, and we call it multi-precision LU. Now, the remaining question is, can it provide a solution to the FP64 accuracy? Let's take a look on the accuracy of the obtained solution. Here in this graph, we depict on the y-axis the residual of the obtained solution using the FP64 standard solver, orange curve, or the Tensor Core accelerated version of the LU with the 3 other colors. As you can see, the solution is not as good as FP64 and most likely will not be acceptable by any HPC application. Well, hold on, there is good news. The good news is there is a technique called iterative refinement that can iteratively refine the solution in order to achieve the FP64 level of accuracy. How it works? You perform an LU in reduced precision, so your solution is not so good. Then you iteratively refine the solution in order to reach the FP64 level of accuracy. You can expect that if this refinement process is fast, you're going to keep the gain you obtained during the factorization. But if this refinement took too many iterations, you're going to lose that gain. Here, on the left side, I represent for you the refinement algorithm. And on the right side, I illustrate the convergence history of the refinement phase for the 3 reduced precision we are studying. The y-axis of the chart on the right side shows the residual in function of the number of iterations for the 3 different reduced precision we are studying. I mean, the TF32, the B-float 16, and the FP16. We can see that after a small number of iterations, they are able to bring the solution down to the FP64 level of accuracy. It requires about 7 iterations for the TF32 and the FP16, and it needs about 16 iterations for the B-float 16. Note, this later highlights the effect of the precision bits on the numerical behavior. Okay, so recently, these type of solvers are getting a lot of interest for the community, and in particular with the existing of Tensor Core in NVIDIA GPU. Many libraries have implemented the Tensor Core accelerated mixed precision into their package, and many research papers are out there. Let's first start by looking how the TKR solver behaved in Volatile V100 architecture. Here is this chart that we have shown before. We depict the performance obtained by the TKR solver using half precision and compare it to the FP64 standard solver. The y-axis of the chart represents the performance obtained in teraflops, while the x-axis represents the matrices sizes. The FP64 curves is the orange one, while the TKR FP16 solver is shown with the cyan one. As you can see, the TKR solver brings 4x speed up over the standard FP64 solver, while providing a solution down to the FP64 level of accuracy. That's fantastic. How about NVIDIA A100? Let's continue and see how the solver will behave on NVIDIA A100 and compare it with Volatile V100. This chart is a little bit messy, but let me walk you through it. The dashed line corresponds to Volatile V100. The solid line corresponds to NVIDIA A100. The colors are consistent through my presentation. Always orange are for FP64, cyan for TKR using FP16, purple for TKR using B-float 16, and green for TKR using TensorFloat TF32. So let's first ignore the V100 dashed curve and focus on the behavior of the TKR solver on A100. So let's look at the solid line. The y-axis shows the performance of the flow, while the x-axis shows the matrix size. And as expected, we can see that the TKR solver using any reduced precision, so using either TF32, FP16, or B-float 16, able to perform A100 about 3.3 times faster than expected on A100. This is great. The speed up trend of the TKR solver on A100 is consistent with the speed up trend observed on the V100. So a speed up of 3.5x over the FP64 counterpart is observed on each of the hardware. It's very important to note that all the solutions obtained by any of the variants are the same, meaning that the solution delivered by the TCare solver with reduced precision has the same accuracy as the FP64 solution. Let's take a look and compare the two hardware now. If we want to compare the same type of solver, meaning TCare versus TCare or standard versus standard, we have to observe the line within the same color and compare the solid and the dashed line. So either compare orange for FP64 or cyan for TCare FP16. The speed up of going from Volatile V100 to A100 is noted in the bracket, and it's almost about 2x. This result, up to now, show very attractive behavior of the Tensor Core accelerated solver. We want to study such behavior and do more experiment with other types of matrices. Let's move to the next problem on the next slide. Here is a harder problem. What's happened? We can easily see that if we use the bfloat 16 as a precision, the solver failed to converge. Why? Well, because for this problem, precision play a big role, which means mantissa bits are needed. For that, the bfloat failed to converge, while both TF32 and FP16 are able to cope with such problem and require a little bit more iteration than the previous example. The interesting behavior here is that even with about 20 iterations to converge, it provides a solution similar to the FP64, and they can still deliver 2.5 times speed up over the standard FP64 precision. This is extremely important for the HPC community. And to emphasize more on the benefit of the TCare solver, we studied the behavior of the TCare solver on a set of real-life matrices arising from a wide area of science and engineering. Some are dense, others are sparse from the sweet sparse collection. We treated all of them as dense. They span a range of between 20,000 to 40,000 of equations. Here on this slide, we depict the number of iterations that was needed to converge to the FP64 accuracy. The y-axis represents the number of iterations, and the x-axis shows the matrice's name. Each color represents the Tensor Core accelerated solver, TCare, with one of the reduced precision. Every negative value corresponds to a non-convergence case, and then the solver will fall back to FP64. If we look at the black line, it represents the TCare with FP32. I know FP32 is not a Tensor Core precision, but to be self-content, I would like to show it. If we evaluate the number of iterations required to make the FP32 precision converge to the FP64 solution, it varies between 3 and 10 iterations. There is one case where it failed to converge, and it fell back to FP64 solver, the first case. However, we do not expect the FP32 variant to bring any speed up. If we want to evaluate the tensor load, the TF32 precision, we want to look at the green square. Here, as we can see, the TF32 passes for most of the 37 cases shown here. It only falls back to FP64 for 2 cases. And if we compare it to the FP16 and bfloat 16, we can observe that TF32 converges faster, meaning it requires smaller number of iterations, which highlight its robustness. How about TCare with FP16? Looking at the cyan circle, which represents the FP16, we can see that they fail for 3 cases. In terms of convergence, we can see that the FP16 behaves slightly worse than TF32, but better than bfloat 16. Also, I would like to note here that the FP16 variant, the matrices undergo a scaling process to avoid out of FP16 range issue. Otherwise, we might see more failure. Staying here with the same topic and looking at the bfloat data, the purple part, we can see that it failed for about 6 cases and is the slowest in terms of convergence. It requires the most number of iterations to converge. We are kind of expecting this from the previous study described 3 to 4 slides back. Okay, so overall, we can deduct that TensorFlow TF32 is the most robust approach for general-purpose iterative refinement solver. Now, what is important for a user is not only robustness, but also performance. So let's switch gear and take a look at the performance. Here, we plot in the y-axis the speedup obtained by the TCare solver over the state-of-the-art FP64 solver for the different matrices represented in the y-axis. One can predict this curve from the number of iterations shown in the previous slide. The TCare using FP32, so the black dashed line, has barely the same speed as FP64, and it falls back to FP64 in one case, thanks to the FP64 Tensor Core unit that allowed the FP64 solver reaching the same speed as FP32 solver. The TCare with TensorFlow, so TF32 presented in the green square here, offers the highest robustness and deliver on average a speed up above 2. It only falls back on 2 cases. The half precision variant, FP16, presented here in cyan color, has roughly the same speed up as TF32, slightly better sometimes, but has more failure. And usually it requires scaling of the input matrices in order to work and avoid out of FP16 branch issue. The B-float variant, the purple color, is the less robust and does not bring any extra speed up over the TensorFlow TF32. So, to recap everything we discussed here, we can conclude that the TCare solver with TensorFlow TF32 is the most robust and the fastest solver. It is the kind of behavior that researchers, developers, and users are looking for. A solver that can bring more than 2x speed up without sacrificing numerical stability. We encourage users to use the TCare solver and benefit from the speed up that can bring to the application.
The TCare solver I talked about here has been released since CUDA 10.2, and some of the new features also were released in CUDA 11.0. What I described here was the LU-based TCare linear solver. There is also QR-based TCare linear solver, which target least square and low-rank approximation problem. And all are released for real and complex system, as well as for multiple right-hand side.
All right. Well,
and please,
thank you. Thank you, everyone. Thank you, Azzam. Let's see. We have we started the whole session about 2 minutes late, so we could use a couple minutes. I think it'd be reasonable if there's any. Let's see, any additional questions. You've been following most of these on the YouTube chat, I think. Let me ask one question. So I would be interested in trying to get GPUs and tensor cores and such to work on different types of operators, not just the conventional linear algebra, with different types of floating point computation, say a max plus instead of a plus times summaring. I mean, could I use these, and of course for the sparse case as well. So when you say sparse matrix multiply, using different types, different operators, lower precision, ideally. How well would the tensor cores? How well could they do that?
So tensor core are actually made to do gems, so small block by block multiplication. So even if you are sparse, if you are able to organize your data as small block, let's say 16 by 16 or 32 by 32 small block, you can do those gems using the tensor core unit.
Okay.
Because it's hardware implemented automatically to perform all those 32 by 32 gems, even smaller, and to one final result C. So we started some work on sparse solver related to this, which means we do the sparse LU, and every time you update your Shur or your frontal side, you do the update using the tensor core and lower precision. So those results are going to be similar to whatever happened. Those the sparse results are going to be similar to whatever is going to happen on the sparse direct solver, where you update using the Tensor Core unit, even on the sparse, because we can transform those sparse into small dense block,
Right.
and then use the lower precision available there.